There are various system calls that can be grouped under different titles. So let's first talk about the system calls related to process control. We need system calls that enable us to create processes from a program on the disk and terminate them, to be able to load and execute them, to get the attributes of a process and also be able to modify them, to set them, to be able to wait for some time or wait for an event to occur, or inform another process about the occurrence of an event, what we call signaling an event, be able to allocate memory, and when we are done with it, free that memory. And as we discussed in the previous chapter, if there is an error, we should be able to dump the core, which is the memory image of that process, at the moment of the error. And if you're doing that, we should also be enabling the debuggers, the use of the debuggers to determine the bugs in our programs. So we should enable how we do a single step execution. Note that this is not an easy task. After each step, you should put something like a pause operation. You're not terminating the process, but pausing the process so that the debugger can access the memory of the process, find the values of the variables and parameters, and display them on the screen for the person, for the programmer who is doing the debugging. And also, if we're sharing data or files or devices, whatever, we should be able to lock these resources so that the processes have exclusive access to these resources temporarily, and then you switch to the other process so that you can share this data or the resources. We also need system calls for file management. So we should be able to create files and delete files, open and close files. Also be able to do these for the directories, don't forget. Read and write files, reposition, which means seeking a specific address in the file, and get the attributes of the file, like whether you have the read permission or the write permission or execute permission for the files, and also, of course, be able to set these attributes. For the case of devices, we should have mechanisms for requesting a device. Like, I want to write something on the screen, so I should have access to the screen for a write operation. Release the device. When you're done with the device, just release it for the other processes. Read and write operations through these devices or at these devices, and again reposition your location for the next operation on that device. Get the device attributes and set the device attributes, and logically attach or detach devices. For example, you can, insert a USB stick on your computer. Physically, it is attached, but you can attach that device or detach it logically. Like, for example, it is, possible to mount the file system on that USB stick somewhere specific in the file system of your hard disk. So it doesn't have to be always at a specific space. Also, we need system calls for information maintenance. Like, we'd like to get the time or date of the system, also be able to modify it. We should be able to get system data, like what kind of a processor am I using, how many cores, what's the size of my memory, what's the ID of this CPU, or the ID of the, for example, the hard disk. That's an important concept, especially for the case of copy protection in applications. Most applications get such IDs to make sure that this application is installed on such a computer. So if somebody tries to copy the software in an illegal manner, it will realize that the CPU ID or the disk ID has changed, and the application will stop running, for example. Get and set process attributes, file attributes, or device attributes. Also, we need system calls for communications. We should be able to create a network connection to a remote computing system, or when we are done, tear down that connection. We should be able to send or receive messages, packets, over a connection that has been previously connected. If we're talking about communication on the same system, we can talk about message passing model, for example. So you can pass messages to a different host also on another computer, or a process on the same computer. So this is typically used in client-server model. Sorry. On the same computer, you can also make use of a shared memory model. So you can have two processes sharing a part of the memory. That's also possible. And if you're doing that, then you also need mechanisms for these two processes synchronizing properly and putting locks on that shared memory, so that when this one is modifying it, this one cannot read or write. So that the coherency of the data item there is preserved. You should have mechanisms for checking the status of your transfer. Is it still in progress, or is it completed successfully, or did it fail? And also attach and detach remote devices. For example, you can mount a remote disk on another device, or then unmount it, such things. Also, we need system calls for protection. So if I'm holding some resources, typically I would like to prevent others from using that resource, at least for the execution time. You should be able to get and set permissions for the resources, for these resources, and you would like to allow or deny user access. You might want to allow a specific user, or a group of users, or everyone, for example, or no one, of course. As we mentioned earlier, the system calls we've been using are generic names. In specific operating systems, they have different names. For example, this is not a complete list, of course, but just for the sake of the example, for process control, in Unix systems, we talk about fork, but the corresponding system call in Windows would be called create process. So here it's exit in Unix, but in Windows it's exit process. So as you see in the table, the names are different. Now, fork is for creating a new process by a process. That means the following. When your operating system boots, remember, first we have the bootstrap working, then the kernel, bootstrap loads the kernel and passes the control to the kernel. And the kernel starts a single process, which is called the init process, which is the mother of all processes. That process needs to create other processes. Like, remember, we cannot start user applications yet. We have to start first the system services. So create a specific system service. Let's say the web server, for example. You have to create a new process. So what init does is it makes the fork system call. What fork does is it creates an exact copy of the current process. Okay? And this process, the copy, now changes itself. We'll talk about that in more detail later. By calling exec, it replaces the executable code for this process with the executable code of another program. Like, for example, the Apache daemon for the web server. So it will read the executable code from that program and make this copy of init the Apache daemon. Okay? So that will start working. That's your web server. And similar for the others. A process is allowed to create a duplicate of itself by making use of fork. A process is allowed to replace its executable code by another one, which means actually completely change the running process by making call to exec, for example. When you're done, you call exit. Uh, when you have another process that you have created, what we call a child process, you might want to wait for it to complete so that after that completes, you're going to do the next thing. Or you might not want to wait at all and you want to continue. If you want to wait, then you would be calling wait. For the file operations, we have open, read, write, and close. These are actually, as you will realize, these are the function names in, for example, C programming language, but they correspond to, each one corresponds to the to another system call in the system. Again, for input-output controls, we have IOCTL, read and write again. IOCTL is typically, for example, controlled for mentioning as an example whether my read and write operations will be synchronous or asynchronous, which means you might say read and the program waits until that read operation completes and then continues. That would be synchronous. But we are also capable of making asynchronous calls for read. That means you say read and control passes to the next instruction, but the read operation is not complete yet. So as long as the next instruction does not depend on the value that's being read, you could actually execute other statements while the read statement still continues. That will speed up your process, but again, you should be very careful with this. You can learn your process ID. You can even learn your parent process ID for a child process that was created. It can learn who created it. You can set alarms and you can go to sleep. That means pause the program for some time. We have, for communications, we have connections between the processes we call pipes. So you can create pipes using the pipe system called shared memory get, memory map. And for protection, we have change mode, which is about setting the permissions of the programs. UMask, again related to setting the permissions, but these are for the default permissions. And change owner, you can change the owner of a program so that you can, for example, let some users use it by changing the ownership of a program. So we discussed this earlier, but let's just repeat it very fast. In a standard C library example, for example, you write your program by including the standard input-output header file, and you write your main function. In the main function, you make a call to the printf function, which is in which has the signature in the standard IO header file and the implementation in libc, for example. And when you compile this program, you will first get the object code. And to get the executable, you should get the compiled object code of this program of yours with the library together, and you form the executable. Okay? When you run that executable, it will start from the first instruction in main, go with the statements one by one, and when it reaches this function call for printf, it will go to the library, the standard C library, and call the printf method there by passing the parameter, a single string in this case, which contains greetings string. So the library function printf in the C standard library will take this parameter, see that there are no other parameters, and prepare the string, put it, for example, in a table, the ASCII codes of these characters in a table, and call the write system call by giving the address of this table, saying write this on this device. In this case, the device is the monitor, your screen. Write on the screen the string starting at this address. Okay, and now it will do the write operation until the end of string character, and when it is done, it will return to the printf function in the standard C library, and printf will prepare its return value and return that value to the function call here. In this case, we have not used the return value. If you used it, you could look at that. And since we are not using it, we'll continue with the next statement in our program. When you're running an operating system as simple as MS-DOS, this is the most trivial operating system you will find. Remember, MS-DOS is a very simple system. It does single tasking, which means it can run only one task at a time. You cannot have multiple tasks running. So there is no context switch between the tasks because there's only one task. The shell is invoked when the system boots. So when you start the computer, power up the computer, it will first go to BIOS for the bootstrap. And the bootstrap will find the command interpreter, which was named, in the case of MS-DOS, it was named command.com, which is actually the interpreter for the commands. It reads the commands and understands. So it works as your shell. And in the command interpreter, you type in the name of the program you want to run, and it will run the program. So it will just load the program from the disk to the memory and run that program. And when the program completes, you will get the prompt again and be able to enter another command. So what it is doing, what the command interpreter is doing, is it loads the program into memory, executes the program, and when it is done, it returns back to the shell. For the case of Unix systems, we can talk about different Unix variants. There are, of course, differences between the variants, but the basic ideas are quite similar. So FreeBSD is an example here. That's what we have in the slide. It's a Unix variant. It's a multitasking system, which means there are multiple tasks at the same time in running state. Of course, for example, if you have a single CPU, single core, of course, at any moment in time, the instruction of only one of them would be running. But still, for example, in process B, you could be running, say, instruction 10. In process C, you could be running instruction 20. In D, you could be running instruction 30. These are all in running state. Like in process B, 9 of the instructions have already been executed. The 10th is to be executed now. And in process C, 19 instructions have already been executed. So they're both in running state. And the operating system is able to switch from one of these processes to the other. So at any point in time, if you were able to take the picture of the memory, you would have the kernel. Of course, the kernel is always running. You would have a command interpreter, your shell, for example. And here in this case, we have 3 processes running, B, C, and D. And we also have some free space. So when the operating system starts, it will start with the kernel. It will start the system services, not shown here. Then your user interface will start. Either a command line interface or the graphical user interface. Let's say, for the sake of simplicity here, we just have the command line interface. So we have the command interpreter, our shell, and from there we start processes B, C, and D. So what the shell would do is the shell first calls fork, as I mentioned a few slides earlier, when shell, like say bash shell, executes fork, another copy of bash will be created. Now these two are exactly the same, but these are two separate processes. Therefore, they have different process IDs, what we call PID. And they are actually, like, if this copy of shell was executing, say, instruction number 100, this would also be starting its life not from the beginning, but from instruction 100. The only difference, as I said, is their PIDs are different. So the fork system call returns the PID of this child process, which is being created, to the parent process who created it, saying the ID, process ID of your child is this value, say 73. And to this one, again, since it's at the same call, it will return a value, but if it returned the same value, 73, also to this one, it would misunderstand and think it's the parent of process 73, although it's itself process 73. Therefore, this one is returned the value 0. Now, no process should be working with the process ID 0 that belongs in it. So no one could be creating process 0. Therefore, this one understands that it is a child process. Okay? That's how the parent and the child differentiate each other. The parent gets the process ID of the child, which is non-zero, and the child gets a 0. And since it gets 0, it understands that it's a child process. Now, the child process makes the system call we call exec and gives as a parameter the name of a program on the disk. That means replace this process, the content of this process, with the content of that program. Suddenly, remember this was a copy of the bash shell. Suddenly, this gets replaced by the code of the program from the disk. For example, ls, let's say. Okay, so this becomes the bash shell, and this becomes the ls program, the binary of the ls program, and it starts executing the ls program from the beginning, from instruction 1, the first instruction in main, next, it will go this way. Now, the shell could say, wait for this to complete, that's a typical case, so it will not display a new prompt until the ls code here completes. Okay, so when this completes, this ls program will call exit, so it will disappear, and the parent, which was the bash shell, will learn that it has completed, the child has completed, and it will continue from there, which means it will display the prompt once again. If the shell, while creating the child process, if it didn't say wait, in that case, while ls is running, the shell would also continue. Okay, so they would continue in parallel. That's also possible. Sometimes we do that. For example, when we want to put a process in the background, typically we don't put an interactive process like the ls program in the background. But for example, if instead of ls you were running your simulation, which would take hours to complete, you could put it in the background so that you get the prompt once again and continue with that. And when the simulation program of yours, which is running in the background, completes, you will be informed about that, and then you can look at the results. The processes, when they exit, they either return 0 to show there's no problem, or a non-zero value, which tells the parent to check what's going on. It typically indicates either an error or a specific condition, whatever.